Hello! So far, we have studied various types of motions that included projectile motion and motion in 1 and 2 dimensions, motion of objects moving in the horizontal direction, motion of objects moving in a vertical direction, motion of objects moving on an inclined plane, and so on and so forth. In this lecture, what we are going to do is we are going to introduce ourselves to circular motion of objects moving in a circle. You may picture the object, the black dot, moving in a circular path, and the circle is centered at origin O and has radius r. And we are going to talk about how the motion is affected as the object goes around the circle. So far, we have also talked about velocity and acceleration vectors, and we have studied velocity and acceleration in the context of them being parallel or anti-parallel to each other. Parallel means when v and a are both directed in the same direction, and that implies that any object with velocity and acceleration in the same direction is speeding up, while the opposite, which is when velocity and acceleration are in the anti-parallel directions, which means they're opposite to each other, that implies that the object is slowing down, right? So you may picture that as velocity vector in blue going to the right and acceleration vector in red going to the right as well. This means that since both of these vectors are directed in the same direction, the object is accelerating, while when both of these vectors are directed opposite to each other, one going to the right, acceleration going to the left, this means the object is slowing down, right? So now we are going to ask ourselves, what if the velocity and acceleration vectors for an object is not this straightforward? What if velocity and acceleration vector are perpendicular to each other, right? What happens if velocity and acceleration are perpendicular to each other? So what does it mean when velocity and acceleration, if they're perpendicular to each other? It just means that the object is not speeding up like it was doing here, nor is it slowing down like it was doing here. Rather, it is just changing direction, maintaining a constant speed. This concept of velocity and acceleration vectors being perpendicular to each other forms the basis of what is known as uniform circular motion. Uniform means that the object traveling in a circle is moving at constant speed. That means the magnitude of its velocity going around in a circle is staying constant. But however, when the object moves in the circle, it is constantly changing directions. It is always turning. And since velocity is a vector, both its magnitude and direction determine the properties of that vector. Hence, if one of the properties is held constant, which is its magnitude, while the other is changing, which is its direction, that means the vector is changing at every single moment it passes through on the circle. Hence, we say that there is a change in velocity due to the change in direction. Since velocity is changing, acceleration, as we know, is defined as the change in velocity over time. Since velocity is changing, we have acceleration, and we call this acceleration the centripetal acceleration. Why? Because anything that's moving in a circle will have the velocity vector pointed tangential to the circle. The acceleration will always be perpendicular to that velocity vector, therefore always be pointing to the center of the circle. Hence we call it centripetal, which means center seeking acceleration. Now the direction of the centripetal acceleration is, as we have just talked about, towards the center of the circle all the time. The magnitude of it is dependent on the speed of the object moving in the circle and the radius of the circle formed. It is defined as AC equals the centripetal acceleration, C for centripetal, is equal to V squared, the speed squared, over R, the radius of the circle. Okay, as always, let's test our understanding of uniform circular motion so far by examining one such problem. We have an astronaut training device which consists of a harness attached to a chair which is designed to spin in horizontal circles at very high speeds. Of course, the chair needs to have an astronaut sitting on it. One such device say, causes an acceleration of 40 Gs. Now, what does this mean? Acceleration of 40 Gs. Well, 40 Gs means 40 times the strength of gravity, or 40 times the acceleration due to gravity, because G, as we know, is constant on Earth, which is 9.8 meters per second squared. The acceleration produced by this device is 40 times that 9.8. All right, that is what this means. If the harness is 13 meters long, what is the speed required to achieve that acceleration? All right, that's our question. Now, how do we know how to solve this problem? Well, because it is mentioned that the device is spun around in a horizontal circle, and so this is circular motion. All right, so let's draw a very simplified diagram of what is happening. So we have something, a pole, an arm or a harness is attached to it. This is the device, or the centrifuge, or whatever you want to call it, and it goes around in a horizontal circle like that. All right, this is 13 meters long, and the acceleration produced is always directed towards the center because it is uniform circular motion. Anything moving in a circle will have a centripetal acceleration, otherwise it won't be moving in a circle. This centripetal acceleration will always be pointing towards the center. Okay, then let me note down what we know. We know that the centripetal acceleration produced by this device is 40 G, which is 40 times 9.8 meters per second squared. What else do we know? We know that the harness has a length of 13 meters. L equals 13 meters. Now, if you look at this horizontal circle I drew, this 13 meters is always constant, right? So all over the circle, this is the 13 meter, the distance from the center to the circumference of the circle. So this is just the radius. So we know AC and we know R. What do we want to find? We want to find the speed that would be required for this acceleration. Okay, we know from circular motion our acceleration magnitude is given by AC equals V squared over R. V is what we want to find, and AC is given, R is given. So we can use this equation. Hence, cross multiply AC to R and V squared to 1. ACR is equal V squared, and V squared, or V, is square root of both sides, square root of AC times R. Now then V equals square root, AC is 40 times 9.8 and R is 13 meters. This comes out to be 71.4 meters per second, a very, very high speed. Now there's a second part of the question which asks us, what is the force that the harness or the arm needs to exert on a 70 kilogram astronaut to hold them in place, right? So what is this force actually? Well, let's draw a free body diagram. Whenever you see the word force, draw a free body diagram. For me, I would draw a free body diagram just for the fun of it. So we draw the free body diagram for this chair. Let's say this is the chair, and the free body diagram looks like, we have the chair right here, an astronaut sits on it. This has mass 70 kilograms, so it will have weight of 70 times G. And then, since the astronaut is sitting on something on the chair exerts a normal reaction force called N that we know by now. What else? Now, this harness or arm, its sole purpose is to make this chair remain in place, right? So this must be exerting a certain force on this whole device. How do we determine the direction of that force? Well, very simple. We know from Newton's law that summation of force is equal to m times a. This means the only two vectors in this equation is f and a. Hence, whichever direction is the resultant acceleration, that is the direction of the resultant force. Hence, since in a circular motion there is always centripetal acceleration, there will always be a centripetal force causing this centripetal acceleration. Okay? In this case, the force is provided by the arm or the harness of the device, and that force will also point in the direction of the acceleration, which is towards the circle. Let's call this force F arm. Our goal is to find what F arm is. How do we find forces? We write down Newton's second law. And first, we have to give this diagram more information. That is, the axis we choose. Let's say we choose upward going positive for y and leftward going positive for x. Remember again, you can choose your axis arbitrarily. So I have chosen the direction of acceleration to be positive, which is towards the left, or towards the center of the circle. In the x direction, what do we have? In the x direction, we have summation of fx equals m times ax. What are the forces? There is only one force in the x direction, which is F arm. M is the magnitude of the m is the mass of the astronaut, so 70 times a. What is a? A is the centripetal acceleration. Okay, so F arm is equal to 70 times centripetal acceleration, which was 40 g, so 40 times 9.8. Therefore, F arm is equal to 27440 newtons. This is the force that the arm exerts to hold the astronaut in place when this device is spun around in a horizontal circle at a high speed and a high acceleration of 40 Gs. Alright, let's look at another example. Here we have a ball tied to a string and spun in a vertical circle. The string is massless, and so we will consider it not having a weight. Ball has mass of 5 kilograms, so let's note down what we know. The ball's mass is 5 kilograms and the length of the string is 0.4 meters. Say the ball is moved with a speed of 3.5 meters per second. This is the speed at which the ball is spun on that vertical circle. The question asks, what is the tension in the string at the highest point? So we are looking for a force. This thing is moving in a vertical circle. Since it's moving in a vertical circle, we don't need an x-axis. All the forces are along the vertical direction. So this is the center of the circle, and this is the string. This is the ball attached to the end of the string, and it's rotated, say, like this in an anti-clockwise manner, and this is the highest point. All right, this is the highest point of its trajectory. We want to know what is the tension here. All right, what is the tension force in the string here? So how is tension directed? Tension, remember, is a pulling force that always acts along the length of the string. So if you attach the ball at the end of the string, the tension in the string will always be pointing up along the rope. It will be pulled towards the center of the rope. So tension in both cases are directed along the length of the rope or the string. So now let's draw ourselves a nice free body diagram. We have the ball here, and considering this is the free body diagram for the highest point of the picture here. At the highest point, what are the forces the ball will have acting on it? The ball will have its weight acting on it, 5 times g, and it will have a tension force acting on it, right? Because it is attached to a rope. The tension force is pulling it downward like this. Denote capital T to be the tension, and now write down Newton's second law of motion. The second law, F in the y direction is equal to ma in the y direction. What are the forces in the y direction? We have both forces going in downward direction. Let's choose our axis. So because all of the forces are directed downwards, let's choose our axis to be plus y downwards, right? Or you could have chosen it upwards, but then you would have to work with a change in sign of the acceleration, which is cumbersome. Then t plus 5g is equal to may. What is the acceleration in the y direction? Remember, a force causes an acceleration. There is a force on the ball, which is the tension, and its weight, and both are in the y direction, vertically downwards at this point. Hence, the acceleration is also pointed towards the center, vertically downwards. So, any center-seeking acceleration would be centripetal acceleration, and anything moving in a circle will have a centripetal acceleration. Okay, so this is how Newton's law changes for circular motion. The acceleration that we knew as the resultant acceleration may be in the x direction or the y direction. For circular motion, this becomes centripetal acceleration. Okay, there's not a new acceleration, it's just how we name it and how it's directed. All right, our goal is to find tension, so let's separate it out. Tension is mac minus 5g. M is 5, so we have 5 here. AC is the centripetal acceleration, and which let's keep it as AC, and plus 5g, meaning on this side it is minus 5g. But remember that what we defined as the magnitude of centripetal acceleration, it was v squared over r, where v was the speed of the object moving in the circle. We know the speed of the object to be 3.5 meters per second. Hence, we can find acceleration centripetal. So we replace AC by v squared over r. And v is 3.5. So we have 3.5 squared over r. R is nothing but the length of the string. The length was 0.4 meters. So this is 0.4. Now we can solve for this, replace g by 9.8, and then we end up with the tension equal to 104.1 newtons. This is the tension at the highest point. The second part of the question asks us, what is the minimum speed required to make it all the way around? So what is the minimum speed required by this ball tied at the end of a string to make it a complete circle and go over this highest point, so go beyond this highest point? So we have to realize that in our free body diagram that we drew for part 1, both of the forces, the weight and the tension on the ball was directed downwards towards the center, right? So in that case, we can say that both of these forces were causing our overall centripetal acceleration. We also know by now that acceleration centripetal is v squared over r, v being the speed. We want to find what the minimum value for this speed is for the ball to make it over the top. Well, the minimum would be when acceleration centripetal is a minimum. When is acceleration centripetal a minimum? If you remember Newton's second law, it looks like F equals ma, and for a centripetal motion this becomes ac. If acceleration is a minimum, then we see that the force must also be a minimum. So a minimum force will have a minimum, or will cause a minimum acceleration. Hence, for the minimum speed, to minimize the acceleration, we need to minimize the force that is causing that centripetal acceleration. We cannot do anything about the weight of the ball because the ball has constant mass, and so will have constant weight on Earth. However, the tension will be minimized as much as it can be. So the minimum value of tension is 0. It can't go any below 0. However, it can be higher than 0, right? So at t equals 0, we can basically find what the minimum centripetal acceleration is, and hence the minimum speed. So then we write down our Newton's law for the y direction again, considering downward to be positive. Now we have only one force, right? MAC. We have only one force, which is the weight. So 5 times 9.8 equal to, M is 5, times AC. AC is nothing but V squared over R. Since we are considering minimum here, let's call it V min. The 5's can go away and we want to solve for V min. So cross multiply R to 9.8 and we have V min squared. Square root both sides to get V min. We know what R is. R is the length of the string, which is 0.4 meters, and this comes out to be 1.98 meters per second. This is the minimum speed that the ball would require to make it over the top or the highest point of this circle. This means that if the speed went any below 1.98 meters per second, then this ball would not make it over the top. It would go somewhere below, because then the weight would be so much to bring it back downwards, right? So far we have talked about uniform circular motion. Remember, uniform was when the speed of the object moving in a circle was constant. However, when we talk about non-uniform circular motion, we talk about objects those are moving in a circle but with changing speed. So the magnitude of their velocity vector is changing. They can be speeding up or can be slowing down. However, circular motion would still mean that the direction of that velocity vector would be changing at every instant. So together we would have a motion that looks like this, an object moving in a circle. However, now we have an additional acceleration, which is caused due to the velocity vector also changing in magnitude. Remember, it can speed up or slow down. This is the tangential acceleration, meaning that the acceleration vector that is a result of the change in magnitude of v is tangent to the circle being traversed, and hence the name is tangential acceleration. But know that AC, AT, these are just different names that we choose to use to tell ourselves that their purpose in life are different. AC would have a purpose in life to make things accelerate towards the center of the circle. AT will result from any increase or decrease in the speed of the object traversing the circle. These accelerations are still accelerations, meaning they arise from changes in velocity, whether it be in direction, which is why AC comes, or changes in magnitude, which is where AT comes in. I hope then this whole lecture on circular motion has made sense.